Hey, Jonathan.
How's it going?
Hey, good. How are you?
Good. It's kind of crazy to say I'm already tired.
Yeah, it happens. We take all summer off and then we get back for a few weeks and then it's already tiring. I feel the same way, but you just kind of get used to that feeling of tiredness.
It's just out of mode.
Yeah.
I don't even think caffeine works on me. And I did good trying not to drink any caffeine during the summer.
Uh-huh.
And then now that I'm back on it, it's like, so I guess it should work on me since I now took a break, but it's ineffective at this point.
I think just your body gets a lot of resistance over time. Coffee doesn't make me more awake. It makes me really jittery, and so it actually has a negative effect. It makes me feel stressed and like anxious for no reason. And so yeah, I usually don't drink that much coffee either.
Probably tea better up.
Yeah. I like the flavor of coffee, but I don't like how it makes me feel.
So what do you do if you don't mind me asking to get that kind of like adrenaline going?
Honestly, I honestly just take a nap for when I need it. My schedule is not so. I mean, as a faculty, the only things that we have to get up for are just the lectures. Everything else is kind of like on my own time, and so like I actually have a lot of like flexible downtime in my office, and so if I need to knock out for like 15 minutes, I'll do that. And I'd rather do that than drink coffee because that'll kind of like ruin my whole day.
That's understandable.
Hey guys. Right.
Yes. Hey. Nixon. I have a quick question.
Sure.
I kind of saw your solutions for activity one.
Yep.
And I was kind of going through what I had, and I didn't get exactly your answers, but they were like off by probably like 2 or 3 like in value.
Mhm.
Is that okay, or does that usually happen on answers?
Yeah, there's always going to be some factor of randomness with finite elements, because how the mesh is generated is always going to be a little bit random. And so I'm not looking for exact answers for these activities. Like the way I design these activities is kind of as an instructional means to like kind of get you used to the software. And so like I'm not testing you on how well you know Ansys, and that's going to come in the project. And so for the activities, I grade them on completion. And so as long as I see that you did everything and then you set up everything reasonably well, then that's all that I'm really looking for.
So with that kind of being said, like if you were to do the activity like in a different like environment, you may get a different value than what you initially got, but as long as you're like somewhere in that range and you're not like if you got 33,000 the first time and you got like 60,000 the second time, then that's where it's like, oh, maybe something's wrong.
Yeah. So there's always going to be differences of like maybe like 1 or 2%. But big differences then that, yeah, then probably something is wrong with your setup. But yeah, depending on the computer that day or depending on how it's meshed, then you're gonna see like kind of small differences between them. Yeah. Mm-hmm.
Professor, we only needed like a specific, we only needed the workbench open. We don't have any specific things to have open.
Yeah, just the workbench. Yeah, we're gonna start from there.
How's your day so far?
It's good. Yeah, it's just Thursday. So this is my last class of the week, and so it's always good.
Oh, you're welcome.
Hmm?
I said you're welcome.
Are we doing that random stick?
No, we're doing all Ansys today.
Awesome. So I'm trying to open up Ansys and it's asking me to allow Ansys and then it asks me for username and password.
Yeah, you can just close everything. So every time it asks you for permission, just close it. So don't click allow, just close it, and then it should be okay. Yeah, people were having that issue yesterday too. So as long as you just close it and ignore it, then it should be okay.
So
Hey guys. Good, good. How are you?
good.
Any plans for the weekend?
No, actually, no. I think I'm gonna relax this weekend.
Nice.
How are you?
Probably a little bit of relaxing and most of the time just working with senior design.
Cool. Cool.
And homework.
Yep, I had to go take the shop test today in order to get access to the machine shop so that I know not to blind myself with welders or kill myself with lathes.
Don't wear,
Sean is,
don't wear long hair.
yeah, don't, yeah, I got to cut my long shoulder length hair.
And kind of, well, a little more bit, but funny is that the one of the things he was explaining for the one of the safety ones were in case your arm gets caught, at least the machine pulling you forward, you'll smack the stop button.
Yeah, he's all doom and gloom on his safety days.
All right, it's 5:30, so let's go ahead and get started today. Good evening, everyone. How's everyone doing today on this fine Thursday? Amazing. Good, good. All right, today is an exciting day. So today is an Ansys day, and so we're going to be going back into the software, right? And so we're going to be working basically completely in Ansys today. And so if you haven't already, I would launch up Ansys Workbench. And then just so that we can kind of hit the ground running. Okay. For those of you in the classroom today, some of these lab computers are having a weird thing with the permissions. And so if you launch Workbench or if you try to do anything within the software and it asks you to give it like administrative permission, you can just close that window and then it should work just fine after that. So I'm not really sure what's going on, but quite a few people, because I ran this activity yesterday for my grad students, and Quite a few of them were running into that issue, but everyone said they just ignored it and closed it, and then it worked fine. So just kind of a weird thing to look out for that. Okay, and so the topic for the activity today is a bike crank analysis. Okay, and so we're stepping up a little bit from our first activity. And so our first activity, we did kind of a 2D analysis on a plate with a hole, and so now we're stepping up into the third dimension. Okay. And so the geometry for this activity is going to be given by, by this figure right here. Okay. I actually got quite a few comments yesterday from bike enthusiasts that said that this is a very strange looking bike crank, and that, not many bike cranks actually look like that. But, it's the CAD file that I have for this activity. And so, whether it's realistic or not, we can debate that another time. But, this is the one that we have for it. Okay. All right. And so if you go to the course website, and you click on assignments, and you click on Ansys Activity 2, okay? You'll see there are several files for you to download here. And so if you click on this link right here, the one that literally says here, why does the color of this change every time I come here? Then this is the PDF. And so this contains all the instructions and all the problems that you have to do for this activity, okay? And so you can definitely download that and take a look, okay? And then the other file that I want you to download is this one right here, which is called crankassembly.x_t, okay? And so everything we do today is going to be working off that CAD file, right? This other file that I have here for you is a bicycle frame, okay? And so this you're not going to use until much later. And so after this activity today, I have an additional exercise for you to do that uses that bike frame. But for today, we're not going to use it. And so the only files I want you to download are the PDF and then the crankassembly.x_t, okay? All right. Okay, and so if you go ahead and download those, okay, then we can get started with the activity, okay? And so with this activity, there's quite a few new things that we're doing compared to our first one, okay? And so kind of the way that I've structured these activities, that every activity is, we're going to learn something new about Ansys. And so, I never want these activities to kind of feel redundant or kind of feel like a waste of time. And so, each activity I think will add just a little bit more. So that first activity we did, I think, is the most jarring because, I think for most of you guys, that's the first time you use the software. And so hopefully every other activity after this, we're kind of adding incrementally a little bit more, okay? And so what's going to be new in this activity is that, obviously we're going to do a 3D analysis, okay? We're going to learn how to import an external CAD file, okay? And so we're not going to be drawing the CAD model inside Ansys. So that's actually going to save us a lot of time too. We're going to be specifying a custom material property, okay? And so I'll show you how to do that. And then besides that, everything else is going to be mostly the same. And so we're going to apply a mesh. We're going to apply our boundary conditions, and then we're going to simulate it, okay? But I'm not going to hold your hand as much this time. And so, I have instructions in here about, how you should do the mesh and everything. But, I'm going to spend more of my time kind of walking around, kind of helping you guys individually, more than us going through every little step together, okay? All right, so that makes sense. Are there any questions? Yes, and so if you can open up Ansys Workbench, you don't have to open up the CAD file, and so we're gonna learn how to import that into Ansys, just in a little bit. But if you can just open up Ansys Workbench, then we can start from there.
So we didn't need to open SolidWorks though?
No, you don't need SolidWorks. Mm-hmm. All right, and so your starting point should just be this Ansys Workbench. Okay? All right, everyone ready to roll? Okay. All right. So let's go ahead and start with Workbench, and then let's go ahead and create a static structural analysis type. Okay. Because even though we're in 3D right now, we're still doing a structural simulation. Okay. And so let's go, just like last time, let's go ahead and click and drag static structural, and then we'll put it into this area right here. Okay. All right. And so now we have our static structural, analysis here. Okay. All right, first thing we're going to do is that we're going to load in our geometry. Okay, and so to import your geometry, you're going to right click on geometry here. Okay, and then you're going to go import, and then you're going to hit browse. Okay, and so what this will do is that this will open up a file explorer on your computer where you can go and look for the file that you just downloaded. Okay, and so let's go ahead and click browse. Well, actually, I need to download it myself. I don't think I downloaded it yet. Great. Okay. So I've downloaded the file, and I think it's in my downloads folder. And so I'm going to right click on geometry, import geometry, browse. I'm going to go to my downloads. Okay. And then I'm going to click on crankassembly.x_t, and then I'm going to hit open. Okay. And if you do that, then then this, you should get a green check mark here next to geometry here. Okay. And then you should see this icon here change to a P. Okay. So is everyone able to import the geometry okay into Ansys? Anyone having any issues? Everyone okay on Zoom?
I have a quick question. So
Yep.
if you have another window open, like it has like section A and then you have section B, is it okay? Because
I would delete one of them, and so just make sure you have one. Yeah. It in theory it shouldn't change anything, but let's just try to make this clean as we can for this one. Yeah. Mm-hmm. Okay. And so I think a fair question is is the file format, right? And so the file I had you guys download was an x_t file. Okay. And so this particular file format is called Parasolid. Okay. And so Parasolid is a great file format for you to import into Ansys. Okay. Because we've talked about before that one of the common ways to use Ansys is to develop your CAD and to make your geometry inside SolidWorks and then import that directly into Ansys. Okay? The unfortunate thing is that because SolidWorks and Ansys are different companies, they're kind of like Apple and the rest of the world, where SolidWorks doesn't like to give out the proprietary code for their SolidWorks part. Okay, and so I think probably what you guys are familiar with is that when you save a SolidWorks part or a SolidWorks assembly, its file format is like SLD PRT or something like that, right? And so unfortunately, this file format is not compatible with Ansys, and so you're going to have to convert your CAD file into a different format. Okay, and you can do that within SolidWorks. It's just you have to kind of explicitly do it. And so x_t, this is a great file format. So Parasolid works really well. It maintains all of the geometrical features really well. Some other ones that work really well that I use often are .igs. Okay, so .igs works really well for importing files. STP works really well. And so the file that the other file that I have on the website is the .stp file, so that works really well. Okay. And then the sister or the cousin file format for that is step. Okay. Right. And so that one also works with Ansys. Okay. So all of these file formats are more open source, and so they both Ansys and SolidWorks can take advantage of them. And so all of these guys should work if you're moving a part from SolidWorks or an assembly from SolidWorks into Ansys. Okay. And so the only thing you have to do is that, in SolidWorks, when you have your part open or your assembly open, you just have to click Save As, and then you just pick one of these. You just pick one of these file types, and then SolidWorks will convert your file into that type, and then you can upload that into Ansys. Okay, but just make sure you convert one of these types before you import it, because if you try to import the SolidWorks part file, then Ansys is going to say, I don't know what this is. You won't be able to do it. Okay.
Good question.
Yep.
Is that Parasolid denoted with that P right there?
Yes. Yeah. So that P right there is for Parasolid. Yep. Yeah. Okay. And so that's imported the geometry. And so, the fact that you have a green check mark here means it's good to go. And so you can actually view the geometry. And so if you right click geometry and you click edit in design model, you can actually view it. And a lot of times it's actually good to view your geometry just to make sure that everything imported okay. But for this one, I've done this activity half a dozen times, and so I know that it's okay. And so
is it just viewing, or do you edit?
You can edit it too. Yeah, and so you can actually view it and you can edit it within Ansys too. And so actually later on we're going to do an activity on optimization, and then we're going to actually use that feature right there, because when you set up optimization, you actually do have to set up some stuff within the CAD software here to do that. So even if you're imported, you have to do that. But we'll cover that later on. Okay. All right. So before we actually launch Ansys Mechanical, the one thing we have to do is we have to create our custom material property. Okay. And so the way we're going to do that is we're going to go onto this this entry right here called engineering data. Okay. And so once you guys go ahead and double click that, and if you double click engineering data, it should bring up this screen right here. Okay. And so last time I had some people that didn't get the screen exactly like this. And so if you're not seeing your window that's exactly like this, you can go to view, and then you can click on reset workspace. Okay. And then by doing that, you should get everything that you see here. Okay. And so we're going to use at least these three here on the left and the middle, but we're not going to use the one on the right. But you want to make sure you have at least these three. Okay. All right, everyone's still with me? Everyone on Zoom still? You have this material engineering data window? Okay, silence means yes. Okay, good. Okay, and so you can see right here that the only material that we have loaded right now is called structural steel. Okay, and so this was the material that we used last time in our Ansys activity, and so this was the the only default that Ansys has. Okay, and so if you want to add a new material, you can either import it from SolidWorks. That's one way. That's one thing you can do, or you can create the material custom here. Okay, and so if you look at this. If you look at this entry right here, you can see that it says click here to add a new material. Okay, so let's go ahead and do that. And the material that we're going to add is one of the alloys for aluminum. And so let's go ahead and type aluminum. Okay, and the specific one is going to be 6061 T6. Okay. This name is flexible, because you're creating a custom one, you can kind of call it whatever you want. But usually it's better to name your materials after what they actually are instead of like Bob or Jim or things like that. Okay, so let's go ahead and hit enter. Okay. And then what you see here is that I've created this new material called aluminum 6061 T6. Okay. But you can see here that there's kind of this blue question mark right here. Okay. And so this blue question mark is basically telling us that we've named this new material, but we haven't actually given it any properties yet. Okay, and so in order to actually use it within Ansys, we have to assign things like the Young's modulus and the Poisson's ratio. Okay? And so let's go ahead and do that. Okay. All right. And so now I want you guys to turn your attention to the toolbox on the left. Okay. And what you'll see in this toolbox on the left here is these are all the different kinds of properties you can give your material. Okay. And so you can see here there's a lot, right? And so you can give it linear elastic properties. Okay, you can also give it hyperelastic properties. Okay, and there's a lot of options there for hyperelastic. You can give it strength properties. Okay, you can give it fatigue properties. So life would be like fatigue. Okay, I do have a brief activity for fatigue analysis later on because I know that's that's an interesting area. Okay, you can do fracture criteria. So there's a lot that you can do because Ansys, you can do all different kinds of analysis here, but at the very least, when you define a new property, you have to be able to define its Young's modulus and Poisson ratio. Okay, and the way that we're going to do that is we're going to assign it as an isotropic material. Okay, and so with aluminum 6061 T6 highlighted, go ahead and double click isotropic elasticity here on the left. Okay, and then by doing that, you'll see the bottom of the screen update here. Okay. And so previously we didn't have anything here because we haven't assigned anything for this aluminum material property yet. But now we get a chance to actually assign stuff. Okay? And so if you click on this plus arrow next to isotropic elasticity, then you'll see that there's a lot of properties that we can define. In particular, we need to define these two guys right here. Okay. And so we need to define the Young's modulus and also the Poisson's ratio. Okay. And you'll see that the boxes are yellow right there. So that's Ansys's way of telling you that, hey, you need to assign this before we can move on. Okay. So any questions on this so far? Okay. Okay. And so now we need to assign a value for the Young's modulus and the Poisson's ratio. So let's go ahead and pop back into the PDF. Okay. And if we look at the top of the document, what you can see here is that our material, aluminum here, will have a Young's modulus of 1 × 10⁷ psi and a Poisson's ratio of 0.33. Okay, so let's go ahead and assign those properties to our Ansys material. So let's come back to Workbench. Okay. And so let's start with the Young's modulus. And so the Young's modulus was 1 E7 PSI, right? Oops, I don't know where it does that. But what you can see here is that the units for this Young's modulus right now are given in pascals, okay? And so we need to change this. And so let's go ahead and click on this plus arrow down here. And then you can change the units for this Young's modulus to PSI, okay? And so let's go ahead and do that because that's what our, that's the units that we're given, okay? And so with this unit as PSI right here, we can change this to 1 E7. Right? And that'll assign a Young's modulus of 1 times 10 to the 7th PSI. Okay. Right, and then let's do the same thing for the Poisson's ratio. And so if we check back on the document, we can see that our Poisson's ratio is 0.33. Okay, and so for the Poisson's ratio, we're just going to manually input 0.33 like that. Okay, and then we're good to go. And so after we've assigned the Young's modulus and Poisson's ratio, you'll notice that this blue question mark next to the aluminum is gone now, right? And so, you know, now that that blue question mark is gone, now we can confidently say that this is a real material. It's like a real boy, right? And so now this material is actually ready to go. We can actually use this in analysis, okay? So any questions on any of this? Everyone's still keeping up okay? Okay. Yeah, question? Oh, okay. Okay, and so now that we're done with this, let's go ahead and close this out. And so if you go to this tab up here on A2 Engineering Data, we can go ahead and close that tab, okay? And then now we're ready to launch mechanical. And so on row 4 right here with model, let's go ahead and double click that. And if you get a security alert, you can just hit cancel. Okay. Okay. And so it's starting up mechanical. And so if you're wondering what Ansys is doing, you can check the lower left corner. Okay. All right, if you're opening up Ansys either for the first time or you're here in the lab, you might get this annoying ad. And so if you get that, you can just click on geometry here on the left, and then you can see your part. Okay. All right. And so here we have our bike crank. And so, you know, this confirms that our geometry uploaded just fine. Okay. And we're ready to go. Okay. And so before I let you go, because you know, I kind of want to let you guys kind of, handle Ansys mostly on your own today. I do want to show you how to suppress parts, okay? And so part suppression is something that you can do, and I always spell this wrong, suppress. Okay. And so part suppression is something you can do if there's, if you want to focus your analysis on just one part of the geometry, okay? And so in our case, the part of the geometry that we're interested in is actually just the crank, okay? Okay. But our CAD file here actually came with some 2 extra stuff, right? And so here we have this rod right here is the pedal. And then we also have this kind of fitting, I don't know if you can kind of see it, that fits the pedal into the crank, okay? And so we don't really care about the pedal or the or the fitting in here. And so we're gonna suppress it, okay? All right. And so if you go over to geometry on the left, and if you hit the plus arrow, which expands the list, you can see all the different parts that we have here, okay? And if you click on the different parts, they're going to highlight in the 3D window for you, okay? All right, but in our case, you know, we don't need the pedal. And so what we're going to do is we're going to suppress it. And so to suppress a part, you're going to right click the part. And then after right clicking it, you're going to go down to this option right here called suppress body, okay? And so if you read the tooltip for this, it says that it removes the selected body from the analysis. And so, you know, we're basically going to say, we don't need you for this, okay? So let's go ahead and click suppress body, okay? And so that got rid of the pedal. And then we also need to get rid of this kind of this fitting right here, okay? So let's go ahead and right click on that and click suppress, okay? And then after that, you know, you should be left with just the crank. All right. Any questions on this so far? Was everyone able to suppress everything? Good. All right. Okay, and so, oh, actually, one more thing. And so, even though we've assigned our material property, or we've defined our material property, we haven't yet assigned it to our part yet. Okay, and so with this bike crank right here highlighted, okay, and so you want to make sure you left click on this. If you come to the bottom left of the screen or the details menu, you should see here that this is where we can actually assign the material. Okay. And so right now it's assigned to structural steel because that's the default. And so you can go ahead and change this to aluminum 6061 T6. Okay. All right. And so now the bike crank is made of aluminum, and you're good to go. Okay. All right. And so from here, you can start on page, what is this? Page 5 of the PDF. Okay. And so on page 5 of the PDF, you should see that there's instructions on meshing, boundary conditions, loads and constraints, and the analysis. Okay. And so from here, I'm mostly going to let you guys go and to let you guys kind of handle this on your own. But I will be going around the classroom, and I will be kind of coming back to Zoom to kind of help people individually. Okay. And so the only thing I'm going to tell you to do is that for the mesh right here, I want you to include at least one method object, okay? Right. And so that's it. This is kind of what it says in the PDF too. And so I want you to assign a method to this guy, okay? And I also want you to assign a sizing, okay? And so this is what you're going to use to change the size of the mesh, right? In terms of the loads and constraints, you need to have at least one fixed support, okay? And so, based on this physical situation, I'll let you guys choose where do you think the best place for the fixed support is going to be, okay? And I also want you to include a force, okay? Right. And the thing with the force, I'm telling you in the PDF that the amount of force that I want you to apply is 100 pounds, okay? So it's going to be a 100-pound force. But I want you guys to decide which direction for the force makes the most sense. Okay. And so think about which direction for the force that you can apply that's going to cause the greatest amount of stress within the bike. Okay, because ultimately what the point of this finite element analysis here is. You want to see, you want to determine basically if this bike crank is going to fail under these loadings, okay? And so in those situations, you want to basically submit the worst possible loading situation so that you can see, if your structure is going to survive that worst case, okay? And so, you can either supply the force in this direction right here. You can supply it in this direction. You can do this direction, okay? And you can even do it into and out of the page too. And so think about, what's the most realistic for a bike crank, for someone kind of pushing down on the bike crank with their foot. And among those kind of realistic conditions, what's going to be the one that's going to cause the most stress, okay? All right. And then for your results, the only results that you really need are going to be total deformation and then also equivalent stress, okay? All right. And so, here's, this is kind of the starting point. And so, throughout today's activity, I want you guys to fill in all the settings for this automatic method, the sizing, the fixed support, and the force, okay? And then if you do all those things correctly, then, you should be able to get the results, okay? All right, and so I'll let you guys go. I'll come check in. I'll kind of gather everyone up in about maybe 20, 30 minutes. And then we can talk about kind of the rest of the activity, okay? But why don't you guys go ahead and get to it, and then I'll cycle around the classroom and I'll cycle around Zoom, and then I'll kind of help people where you guys need it, okay? All right, and so if you're in the classroom, you need help, just raise your hand. On Zoom, just type something in the chat, and I'll come back to it. Okay.
I have a quick question.
Sure.
So what if on the case we need to import like a 2D object, will Ansys automatically update it in its properties to 2D, or would we have to manually do that?
It should. And so in SolidWorks, I think that you can create like a thin shell structure. Then Ansys should automatically recognize that. Yeah. Mm-hmm. Yeah. Okay. Yeah. So the units. right? So you can change the units here. So actually, you can change the units to be kind of whatever you want that's convenient at the time. And so like yesterday when my grad students were working on this, when they were setting the mesh, they actually found it more convenient to assign the mesh sizing in terms of millimeters, okay? But then when they got to the force, then obviously they need something in pound force. And so they switched it down here. And so the nice thing is that whenever you switch units within Ansys, it'll automatically convert, everything before that. And so, you can kind of switch around the units based on what's convenient for you at the time. And so, I think kind of the worry that people were having is that if they switch units here, is that going to mess up stuff over here? But it's not. And so, whenever you switch units, it's going to automatically convert stuff. Yeah. Feel free to guys work together too. So, you don't have to work in silence. So. Yes. Oh yeah. So when you guys get to the mesh, I think in the activity I asked you guys to do a hexahedron mesh, and so the way to do that in Ansys is to set it to be hex dominant. Yeah.
Dr. Tran, for when we're selecting the mesh using the method that we added, it says to select hexahedrons,
Yes.
but the element order that I'm selecting for that does not give me hexahedron.
Yep. So the hexahedrons is going to be from this method right here. So it's right now it's grayed out because you need to select a body. And so if you select this entire body like that, you hit apply.
I see.
Yep. And then now you can change
I
it.
gotcha.
Mhm.
Oh, I see. So it does only say tetrahedron.
Yep.
When you mean quadratic order, are you referring to all quad for the three-phase mesh type?
No, so the quadratic order is this one right here. So the element order.
Oh, okay.
Yeah, and so here right now this is the global setting, and so I want you to change this to quadratic. Right here.
So then just leave the mesh type to be quad and tri.
Yeah, that one, that's fine. Mhm.
Oh, I get it. You select the quadratic, then the hex dominant shows up, allowing you to select that one from higher.
Yes. Yeah. Mhm.
Like, okay. Cool.
This error message saying that geometry selection is required. Selected this geometry.
So right now your boundary conditions aren't set yet, and so you need
Oh, I
to
thought
set
I
the
could
boundary.
just run the mesh just to see if it
Ah.
works with the hex.
If you wanted to check the mesh, you can right click the mesh. I guess right there is fine. So just the generate.
There we go.
Yeah, and then that's what
Cool. So that seems like it likes the tetrahedron
Yeah.
or the hexa.
Yeah. No, that was good. So the hexahedron or the hexahedron referred to kind of the shape of these blocks. You can see it looks like kind of like
Yeah.
Yeah. So that's what a hexahedron is.
Cool. Excellent. Thank you very much. I'm trying to.
What was the error that you got, David?
Accidentally clicked out of the error page. Oh wait, it says it just says the measure failed to generate, and then
Try making your elements a bit smaller. So the thing with hexahedron meshes is that they're a little bit hard to it doesn't always work for every geometry. And so, kind of the solution for that is just to make the elements a little bit smaller. Yeah, so go to your sizing object and try to make it a little bit smaller than that was before.
all right, I'll try it out.
Question.
Yep.
For the refinement, since we're working with 3D, would we be choosing like the inner part of the shape?
Yeah, no, it's a good question. So in refinement, when we did that for the 2D case, we chose an edge basically. And so for 3D, you can actually do both. And so you can actually do an edge, or you can choose a surface. Surface will be a little bit more stable because then it has a bigger surface area for it to refine around. But you can do an edge too, and it should work too.
And if we were to do the edge, we would have to choose both sides. We have that possibility to choose both sides.
You can choose multiple surfaces too. And so if you hold control on your keyboard, you can click multiple things. But technically you don't have to, and so you can just refine around one edge, and that's technically okay. But if you want to do select multiple ones, you can hold control and then click multiple surfaces. Yeah. Oh, interesting. Why don't you share your screen, and then I'll let me take a look.
I would share my screen, except I have the Zoom open on my other computer and then like my Ansys on the other one.
Oh, okay.
Sorry.
Can you just can you take a screenshot and then send it to me?
Yeah, sure.
When you're trying to select hexahedron, is that the same as hex dominant?
Yes, yeah. Hex dominant is the same as hexahedron. Yeah, the reason it does that is because it's it's really hard to get a full hexahedron mesh usually on a geometry, and so sometimes it has to place some triangles and some tetrahedron there, but it'll try to do mostly hexahedron.
Hey, Professor, when something's fixed, it can't rotate or translate, right?
Correct. Yeah.
So why would this be fixed at all if it's a crank?
Yeah, no, it's a good question. And so we're doing kind of because in reality, the crank is rotating, kind of like what you say, but we're doing kind of like a static analysis of that.
Okay.
And so we need to fix it at some point, and whenever you do a structural simulation, you need to have one fixed support, because otherwise it's going to either rotate or translate in space. So we want to make sure that it's completely fixed.
I see what you're saying.
It's a static approximation of a dynamic situation.
Got it.
Yeah. Yeah.
Velocity, we did it just on the whole.
Yep. So I would recommend that you try running the simulation first before you add refinement. So generally, where you want to add refinement is places where the stress has been concentrated. And so areas of stress concentration, that's where you need refinement. That's where the solution most likely to go. And so generally, for the first activity, I have you guys going to do it preemptively. But what's more realistic is run the simulation. You say, yeah, I have high stresses here. Let me refine that. So, yeah, try running the simulation first, and then you can decide where to go.
Okay. It changed everything in the triangles. When I tried to refine it.
Yeah, so that's the thing. So when you add refinement, it changes everything to triangles. And so you can't do refinement in text. So that's kind of one thing.
Okay.
This is the same assignment we're going to be submitting for.
Yes. Yeah. All right, David, I got your screenshot. Let me take a look. Huh. I don't see anything. Oh, so to change the units, you can do it from the home. So actually, let me share my screen one more time. And so from your home, and so you're on the home home tab up here. Okay. And then you can change the units right here, basically. Okay, so you click down here, and then you can change the units to pounds right here.
Okay, thank you. I'll try that.
Okay. David, can you try just suppressing this one for now? And so if you go to your hex dominant mesh, you just go ahead and click suppress, and then see if you can create the mesh like that. I think if I remember from last year, a couple people had some issues with the hex dominant mesh too, and no matter what they could do, then it wouldn't work. And so it might be a computer specific thing. Yeah.
I think I may have the same problem.
It's not generating the hex.
Well, at first, like, oh, go ahead.
Yeah, because go back to your siting. Because right now your siting is 5 meters. So what you're saying is each element is 5 meters big. And so you want to make that multiple. So go ahead and change the units to 4 meters. Yeah. So try lowering it. You have to uncheck it. So you see the little view there. Now you can. Same issue with the hex.
Yeah, so originally I did the refinement, and then I did I generated the image, and it just became that.
Yeah.
And it's refinement, and update this and it's still staying the same.
You might have to just regenerate the mesh. So right click on the mesh. Yeah, because unfortunately the refinement only works with tetrahedrons. It doesn't work with the hexes. For this activity, it doesn't matter all too much. You're going to get probably the same thing. It's good to know.
Am I able to have like reset the entire parameters from the mesh?
So you can delete. So you can delete the method object, but you can delete the or try suppressing. And go ahead and write the generator. And then try unsuppressing it from that. Okay.
Okay. Thank you.
David, did that work when you suppressed the hex dominant? Were you able to generate a mesh?
Excuse me, Professor. I have a question.
I wasn't able to get mine to work.
Oh, okay, Jasmine. So I see someone has their hand raised in class, but let me help David first, and then I'll go to you.
Yeah, I was just not paying attention. Sorry.
Okay. Yeah. Or David, sorry. What did you say? Oh, David, did that work? All right, I'll come back to you. If it worked, say it worked in the chat, and then I'll see it. Yep.
So this load, like how does that center like is this what's fixed to the next part, or is it fixed to the bolts?
So the way I kind of interpret it, so the kind of the real answer is that you're going to get kind of the same answer either way. But the way I kind of interpret it is that it's fixed on these two, and then it's kind of rotating around this one. So this one's kind of like it's like a crank of it. This sword's actually fixed.
Okay, so
actually in the past when I've done this, I've just fixed all three. And then you get kind of the same.
and then so if I want to do all three, you said shift
Control.
So
Yep. And so now you have CC two faces. So those are the two faces.
But then it deselected this.
Yes. And so whenever you put apply right here, it just applies whatever selection you have. So just overwrite something else.
I have a question. Yeah. So what's the difference from changing that one side here to one side?
No, it's a good question. So when you set the siding on this mesh right here, it's going to change it for the entire assembly. And so for this analysis, we only have one part, so it doesn't really make a difference. But the reason I'm teaching you to do it from here is that in the next activity, we're going to have an assembly of stuff in place. And so you can choose the siding for each individual. But doing it from the mesh, then it's the entire, which is fine if you want to do everything, but sometimes you want to have kind of more fine grained control.
So I was kind of lost and I changed it on the. So it doesn't matter.
Yeah, for this one doesn't matter. But I just want to make you aware that this is something because we'll definitely use it in the next. I think only two different parts, but in those two parts we can assign different mesh size.
Okay. Cool. Sorry. I keep trying, but my window on the chat it's not open.
Oh, so you might have to reset the workspace. So go to display. Show statistics. You maximize the window. Someone had this issue. Someone it was like hidden somewhere here. Go to show. Oh, okay. Yeah, so go to next. Yeah. Oh, hey. Oh, the audio is coming. Oh, sorry about that. So I was asking you, did it work when you suppressed the hex dominant method? Were you able to generate a mesh? Let me just message you. Okay, yeah, try, yeah, you can try making it smaller, but you can try suppressing that one too. All right, Jasmine, you had a question, right?
Yeah, actually, I had a question. So I was wondering, like in Ansys, is there any way we can just measure the thickness of the bike crank? Because I thought like if I just put like by accident like a 0.2 inch for the mesh size, and I think I'm getting like exactly 2 cubes on the thickness of the bike crank. So I thought like maybe the thickness is 0.4, but I don't know like if there's like any tool we can measure it.
No, yeah, no, it's a good question. It's definitely useful because a lot of times you want to choose the mesh to be kind of the same as your you know, as your thickness. I know in Design Modeler there's a way that you can measure stuff, but I don't know if there's, let's see, size.
I actually opened Design Modeler. I just want to know. I guess that it might be possible to just do that, but I don't know like where it is in Design Modeler.
Oh, actually, if you open up the part within the other CAD software, which is Space Claim, and so there's a measuring tool in there that's pretty intuitive to use, and so that I know that one just because we're going to use that one for a future activity, but for this one. Yeah, for Design Model, I'm not sure where the measuring tool is exactly.
It's actually deactivated the Space Claim for me. I don't know why. It's just like click on it. It's not.
You might have to close. You might have to close Design Modeler in order to.
Oh, I see. Okay.
Yeah, because I don't think you can have both open because in theory, if you can use one to modify the geometry, it's going to affect the other one, and so it probably just prevents you from opening both.
Yes, actually makes sense. Thank you.
All right, how's everyone doing? Was everyone able to, are people able to get to some simulation results? See the information? Cool, cool. In about 5 more minutes, I'm gonna just kind of go over the rest of the activity for you guys. And so, no matter where you are, it's kind of okay. Because I do want to discuss, what you should do for the rest of it. Okay. So 5 more minutes, I'll bring everyone back.
Could you check out my results?
Sure.
So I fixed over here and I did a downward force inside of here.
Okay.
Pushing straight in. So this looks okay, but it's not really deformed as much as I expected.
Okay. So let me see the
normal stress or equivalent stress. Equivalent stress looks exactly the same, except I put the fixed force on this side right here. So that's
okay.
That's really changed.
Let me see the direction for your force. So you put in which direction? Y. Okay. Great. Okay. So actually, and so that's interesting that it's. Let me see your equivalent stress field again.
It's fixed on this side.
Yeah.
I should have fixed inside of it, not on the back.
Oh,
I did the
okay.
edge inside right there.
I see. So all your stress is concentrated right there. That's really interesting. Wait, let me see the force. Did you apply it on the head, on the face? Okay. So actually for this project, I actually fixed it on the opposite side, and so I fixed it over here where it's attached to the bike.
Fix it over here.
Yes.
Isn't it attached to the bike right here?
No, it's attached to the bike because this is where the pedal is.
Okay, I did it backwards.
But the direction's right, and so the direction should be the minus y. And so actually, what you should see is that the stress should be kind of concentrated around kind of the neck right here,
which I'm not seeing. Right? Oh,
yeah. Yeah, it's interesting though that the stress you're having it kind of concentrated around that edge, which I've never seen before. But yeah, try switching it and seeing if that
switching the fixed and the force.
Yeah. So switch the fix over here and the force.
Okay, sounds good. Thank you.
Yeah. Oh, I have no idea actually. I'll check your site. Okay. I'm wondering, so this one should override that one, so we have 2 different ones. This one should override. That's what it should. So if you do that. Oh, yes. This looks like about 3 million.
And this is fine.
Yeah.
Yours is triangle.
Oh yeah, because I was texting something, but David was sending it to the text on it. So I was showing this. This looks great. Yeah.
Oh, yeah.
Yeah. It's a. Oh, okay. Yeah. So I would recommend you try getting simulation without refining first. So try getting the boundary conditions in. And so what I've been telling people is that usually you want to have refinements around the places where you have stress concentration. So there's high stress. And so we did that in the first activity. But for this case, I want you to run first and then try to see where you have stress. But even then, for a lot of cases, it's not really necessary. So actually, for this activity, I personally didn't add any of it. It still was fun. So try to get through it all first. And I'll show you where you go.
So my question, so I put the force inside of here.
Yeah.
But in like a real application, the force will only be applied directly in the center and the bottom half of the circle.
Yeah.
The whole circle.
No, yeah, it's a great point. And so yeah, in reality, when you push down on the pedal, it would only stress these small portions.
Yeah.
And so it's a little bit of an approximation to do the whole one. There's a way where you kind of break up that surface and so that you can only put it in there, but it's a little bit annoying to do. And And we'll learn how to do it later on, probably pretty late in the semester. But for now, you can kind of just on the whole time. Yeah. And so what you'll see is most of the action is going to be over here. And so, or most of the stress concentration. And so what happens over here doesn't make too okay.
And you said over there, I just get rid of my refinement?
You technically, I mean, if you have it already, it's fine. And so I'm not going to tell you to get rid of it. But for this activity, you can still get really good results.
Would you say another activity that should run first before I do the refinement?
Yes. Yeah. Yeah. Because generally what you want to do is you want to find the areas where your stress is concentrated. You have high stresses.
Yeah.
And that's typically where you want to do refinement. But even then, so like if you look at your stress field right now, yeah. So if you look at kind of you zoom into that area, so what I typically look for when I want to add refinement is I look to see if the stress distribution is smooth. And so what I mean by that is, right now you see it's red, but you have this like really nice smooth transition between red and orange.
Yeah.
And so that's generally most of the time you have kind of really smooth stress distribution.
By that you mean by smooth transition, then like you can see the border between red and orange.
Okay. Yeah. And so, because what can happen sometimes is that, actually, you saw it actually with your previous simulation. So around that hole, like the stress distribution was a little bit jagged, right?
Yeah.
And so it was like kind of like, I call it like splotchy. And so you have kind of like red, and then suddenly it's blue, and then you come over, it's like green. When it's like that, that's when I would try to add refinement, because that's when I said, okay, the stress doesn't look smooth like this. So you want to get kind of smooth stress distributions.
Got it. Thank you.
Quick question.
Yeah.
For the units, what I
yes.
And I have a question for my geometry. Some reason, since it's 3D, do we have to choose like the plane that we're working with, or can I choose the whole body as a geometry?
So for the force right here, you're choosing the location on the junction where you want to apply. And so if you chose the whole body, you're going to put a full force on the power. But for this case, we don't want it. You want to just put the force here, which happens. So I'll switch it to that surface case, and then you put on one of the interior surfaces. It doesn't matter too much which surface you pick because it's all intelligent. You can choose this.
And also, I'm trying to apply it now, so if you would put a negative value.
Correct. Yeah. Okay, so I do want to bring it back for just a second. And so kind of no matter where you guys are in the activity, let me go ahead and just kind of summarize where I want you to take this, okay? Actually, let me finish this up for myself, actually, just so that you guys can see. Select this one here. Force. So let me go ahead and run this. Okay. Everyone on Zoom still with me?
Yes, we are.
Good. Okay. And so when you run the simulation, you should get something like this for the stress field. Okay. And actually, let me change this to PSI. Yes. Okay. All right. And so you should get an equivalent stress field where you get a stress concentration over here, okay? Right. And so this is kind of what you should expect, okay? And so, the question is, what do I want you to do with these results, okay? And so if you go back to the PDF and you go down to problem 5, okay, you'll see that I'm asking you to find what's the maximum load that this bike crank can handle, okay? Because right now we're applying a load of 100 pounds, right? And so we're applying a 100-pound force this way, okay? And then what that's producing is it's producing a stress field that has a maximum equivalent stress of about 13,355, okay? A question in the chat? I'm using tetrahedrons for now. It's if you have it in hexes, that's great. But for this one, tet should okay. The only thing is you need to make sure that you have quadratic elements. That's the most important thing. Okay. And so if we go back to the PDF, what I tell you here is that the aluminum that you're using to make this bike crank out of, it has a yield strength of 35,000 psi. Okay. And so if you remember from a couple lectures ago that, what the yield strength basically means is that if the equivalent stress ever exceeds the yield strength, then that bike crank is it's gonna break, okay? And so what I want you guys to do is I want you to basically, increase the load until you get a maximum stress of 35,000, okay? Or actually, it's not 35,000 actually. So I'm telling you guys to work with the safety factor of 2.0, okay? And so what that means is that, I want you to find the load or the force that you can apply until you get a maximum stress of 17,500 PSI, okay? And so that's your target, okay? And so if we go back to Workbench right here, or to mechanical, right? And I go to this force, and right now you can see that the force that I'm applying is 100 pounds. And so if I increase this to, let's say, 120 pounds, okay, I rerun the simulation. And so I basically increased the amount of force to 120 from 100. You can see here now that the maximum stress is increased, okay? And so before it was about 13,300, now it's about 16,000, okay? And so we're creeping a little bit closer here to 17,000, okay? And so to get even closer, I can increase the force even more. And actually, no, I won't, because then, because I know what the answer is, and so I don't want to get too close too close to the answer. But basically, what I want you to do is, once you have everything set up, then you can keep modifying this force and changing the amount of force that you apply until you get a maximum equivalent stress of 17,500. Okay, right, and then that's going to be the answer to that problem, right? And so once you find that force that produces this stress, then that's going to be the answer to number 2. Okay.
How do we come up with the number of 17,500?
Yeah, so the 17,500 comes from the fact that for the aluminum material that you're using, the yield strength is 35,000, right? And so so once the stress reaches 35,000, then the bike cranks, the aluminum is going to fail. Okay, but then I want you to work with the safety factor of 2, and so we're basically cutting that force, that stress, in half, so that we have a little bit of margin to play with. All right, does that make sense to everyone? Any questions on that? Okay. All right, and so that's problem 5. Okay. And so for problem 5, you're supplying the force here in the y direction. Okay. But in problem 6, I want you to find the maximum load that it can sustain in compression. Okay. And so what that means is that I want you to change the direction of this force. And so instead of being in the negative y direction, we can instead supply it in the negative x direction. Okay. And so if I change this to this x component force to negative 100, now the force is basically compressing the bike crank this way. Okay. And so, if I run the simulation with the compressive force, and so if I run the simulation with the compressive force, you can see that the stress is much lower here, right? Because we're no longer in bending, and in fact, it's a lot lower, right? So in fact, the stress that we're getting is about around 1230. Okay, and so looking at that, you can actually increase this force quite a bit. And so let me increase this by 1,000. This one I don't know what the answer is yet, actually, because I haven't done this part, but I do know that in compression it can sustain a lot higher forces than in bending. Okay, right, and so you can see I've increased the force from 100 to 1,000. And you can see now that the maximum stress is much higher, and so we're a lot closer here. So let me do one more. And so let's try 1,500. Okay. Okay. All right, and so with the force of 1,500, then we went over a little bit, okay? And so the maximum force that it can sustain in compression is somewhere between 1,000 and 1,500, okay? And so I'll let you guys kind of play with that and try to find the exact number. Okay? And so that's problem 6, okay? And so there's a second problem 6 because I'm bad at numbering and I'm kind of kind of an idiot. But in this problem here, what I want you to do is I want you to take the results of what you found in problem 5 and problem 6, and I want you to put it in a way that you would basically communicate with your manager for it. Okay. Because a lot of times, when you're working as a finite element engineer, your manager or even your coworkers are not going to want to look at pretty screenshots of your work. And so what they want to do is they want to basically get just the main points of your analysis. Okay. And so in problem 6, basically what I want to do is, imagine you're kind of writing an email, you're writing a report to your advisor or to your manager to basically tell them what you found from your finite element analysis. Okay. And so, the point of this is to kind of get you guys in the habit of, how do I express my finite element results in writing, to kind of give you a little bit of practice, because, we do have 2 projects in this class. So we have a midterm project and a final project. And so this is kind of your chance to kind of get a little bit of practice of, how do I take, these finite element results, which are, normally figures, and then communicate them in a way that's kind of parsable to someone who may not be an expert in finite elements. Okay. And so for this one, it's just the first one. And so don't stress about it too much, but, try to write it to someone who, may not know anything about finite elements. Okay. And so think about yourself maybe about a month ago and say, if I were to write an email to myself a month ago explaining what I'm doing here, then that's how you would approach this thing. Okay. All right. And then problem 7. And so the very last one, I want you to do a separate finite element analysis on this bike frame. Okay. Okay. But I thought about it before the lecture today, and actually, and so I'm making all my grad students do this because it's, they're a little bit more advanced. But for you guys, since this is kind of the undergraduate version of finite elements, and I'm already asking you guys to do a lot already, I will make the very last one optional. Okay. And so if you do it, I'll give you a little bit of extra credit for it. And so I'll give you a 10% bonus on the points for this one if you want to do that one. But you don't need it to get full credit. Okay. And so I'll send an email to confirm that, just because it's, because I know that there's kind of a lot already, and I want you guys to make sure that you get everything else done first before you tackle something like that. Okay. But if you do want to do it, then there's instructions for you here in order to do this analysis on this bike. Okay. All right. So any questions on any of this? Okay. All right, so that's all I had planned for today. And so I know we still have a little bit of time left. And so, if you guys still want to keep working on it, I'll stick around for the next, 20, 30 minutes just to help people out. But, if you want to work on the rest of it on your own time, that's fine too. So thank you guys for tuning in today. Hope you guys enjoyed the activity today. Have a great weekend, and I'll see you guys next week.
Thank you, Professor.
Thanks, guys. Oh, yes. So go. Normally when you say it, it'll say it's a little bit difficult to. Yeah. And even when you do that, it messes up the with this stuff, it kind of seems like one. I think you need to. Yeah. And it'll take us one file, and you can put that one file onto it. So this is you can always figure out this. And when you if you're recording it from this, you have to kind of load it. Oh, I think you have to save the project first and now. So this is the project. Okay. So you want to load that file again for a project. So it'll take a little bit of time for us to but then this is a little bit this is more convenient than trying to save the file. So, yeah. So Actually, we just actually, I should be this one. So it should be the one that's, you said it you don't want this, yeah, for this one, it's, I would check the direction of your force. Well, this is pressing. Also pressing. Okay, okay, yeah, right. Yeah, that's all. Okay. Yeah, so that can happen sometimes with what's warning that the definition is so high. That, remember we talked about when we use the definition. When we are asked to see, it's only good up to a certain amount of definition. And so this is just a one. So for that one you can kind of ignore this. 25,000 was really big actually. So yeah, it's just a one. So that one is normally the rest of that. There's an option within the Ansys that will go over later on. Yeah, it says that. Yeah, yeah. So it'll make the simulation more expensive, but it'll be more. Okay, cool. Yeah. Yeah. Yeah, yeah. So it's so it'll be at this point it'll be quite less. All right. Thank you. Yep. So I noticed, like, you know, I don't want to use specific I was shooting but I couldn't right here and somehow make the force going to the side. Oh, it's just there's some render. So it's actually taking that force and distributing it over the whole surface. The arrow kind of I've noticed it moves around kind of watching. But it's actually distributing over the whole surface. So I think where the arrow is kind of it's actually distributing over. Okay. The arrow is just for and so, you know, what I'm looking for usually in the stress is notice like there's kind of a very simple definition. I see red, orange, yellow. That's usually good. So, you know, you'll copy the very next study. And you look at situations where the stress looks really kind of genuine. I call it scorching. And you'll see like red, blue, green, yellow. And so when the stress is then that tells you that something's wrong. So when it's kind of your separation, it came out on this one. Is that just your mesh and the mesh size? So that's when I did it with compression. Oh, and even I don't think that might not be because if you look at the stress, it didn't look quite. It should look kind of. So it's sorry, I just keep but then but then I guess yeah, in this case you have to go sorry. So I would only have for this case it's I have to get good week. Thanks, you guys too. Have a good weekend. See you, we'll see you whenever we work on this. Probably best to yeah, no, that's a great so if you decrease the only side, you'll probably see the change because it's generally you're going to get a little bit more experience as you refine. And so you'll see it change a bit, but you know if it's not changing, and so usually I go like sometimes people get this. But 13,000 versus 13,290, you know, that's not that. It is changing less than like 2% basically the mesh that's usually Yep. There's no right or wrong answer for the positioning of meshes and static structural. What do you mean by positioning of meshes?
Like selecting the refinement and the well, I figured that for the meshing, I selected this on my screen.
Oh, let me look at your screen.
Yeah, I selected this for my mesh, the front and back.
Yeah.
And yeah, I just wanted to see if like if there's really no right or wrong answer for selecting the type of mesh. It's just based on my own analysis.
Yeah. And so so generally, where you want to add refinement is and so I've been telling people in the class this, that when you add refinement, you generally want to add it on areas where there's stress concentration. And so if you have a stress concentrator somewhere, that's usually a good idea where you want to add some refinement. And so you can kind of use that as your guide. But it's not a right or wrong thing. It's kind of, it's more kind of your judgment as kind of the finite element engineer about where you need refinement or not.
Okay. And one more question. The force, the same is being applied to the location of the force that we deemed it to be?
Yep.
All right, because I noticed that you simply selected this interior side, and for me originally I selected this and the interior as well, because that's kind of where the pedal and the part were residing in. So I figured that like, well, that's where the most of the load's being applied to.
Yeah, I think yours makes a little bit more sense because the pedal is going to be compressing on both of those things. I just picked one just to kind of make it fast, just so I can get. But yeah, I think it makes more sense to distribute it across all of the surfaces. But
all right.
But I think for this activity, if you do either one, you're going to get very similar answers. But kind of speaking purely physically, I think yours makes a lot more sense. Yeah.
All right, cool. All right, awesome. Thank you very much.
Yep.
Professor, how close to 17,500 would you like us to be spot on? Or
it's going to be really hard to get really spot on. And so if you get within like, I would say 2% of it, then I'd say you're good. Get the first 3 sig figs. Let's say that. And so if you get 17,500 something or 17,400 something, I'd say that's good enough. Oh.
I have an issue with like my display. You know how to fix this?
Oh, it's like that. Other people have had issues with that too. I've never been able to recreate it though, and so I'm not really sure what to say. I remember one person had that issue last year, and then our IT person said to check your resolution.
Okay.
But she never followed up, so I don't know if it actually fixed her.
What I've been trying to do is I just go here, properties. I've been playing around with that compatibility.
Okay. Okay.
I saw like on some forums you have to mess around with it. It really depends on the computer.
I see.
So I don't know. I probably have to mess with it.
Okay. Yeah. Play with the resolution. Play with the compatibility. Let me know what you find too, because I've never been able to recreate that myself. So
Okay.
I never know what to tell you.
Yeah, because when I get home, I just connect it to a Mac. That kind of like blows up my screen, so I have to like mess a few things. But that's the only one I'm still trying to figure it out.
I see. Okay. Yeah. Let me know what you find, and then because I know at least one other person's having that issue.
All right. So, cool. Thank you. Quick question.
Yeah.
Would we be able to apply forces at an angle?
Yeah, you can. And so if you go back to your force, and so you can have both x and y. So if you say put like 100 for x, or both 100 for leave the y component alone, and then leave the and then change the x components. So now you see that the force is being equal. So you're literally applying the force vector. So you can point the vector to show based on the group.
But that's okay. Based on our angle, we would have to sort it to the
Yes. You might, so I usually do it because components usually make the most sense. But actually, if you change the define by, so instead of components, I know there's a vector. I'm guessing you can click it this in order to I've never used it before, but supposedly you can click it, you can click and drag the stroke if you want. I'm not sure how it works in 3D space. For me, it's usually the simplest just to break it down. But then you know exactly what
Oh, yeah.
Oh yeah, Dr. Tran, you mentioned someone was having